Surveying. This will be one of your survey sites. We're going to be surveying across the creek. Here, the whole idea is to get a profile, a cross-section of the creek, and you'll come across the creek and you'll go up onto that level up there. So you're going to survey a cross-section through here. Okay, so I'm going to teach you about how to use the equipment next week. We'll start then, and then you can do your surveying the week after and break up into groups. I think we have 7 dumpy levels. So we're going to be using dumpy levels in this instance. I'll talk more about that next week, as opposed to a theodolite or a total distance station or some of the other GPS type surveying equipment that we've got. So this one was sort of a class set one. So yeah, I'll show you how to do all that next week. But the idea behind surveying the creeks is if you're going to do 2 cross sections, one there and one down near where we first crossed the bridge coming over here, just after we came out of building E1, and you're going to survey a cross section through that area there. Now, that channel there is much wider and deeper than the channel here, for good reason. It's at the confluence of 2 streams, so where 2 streams have come together. So there will be a greater discharge there. There will be more water flowing down that stream. Have you had any lectures? I don't think you have you, on fluvial geomorphology? So you know what I'm talking about when I talk about discharge, QPEC, and various, hydraulic radius and all of those terms. It doesn't mean anything to you? Sorry?
Only first year stuff.
Only first year stuff. Okay. Well, I think Chris is going to take you through a fair bit of that in lectures after I finish. I will finish next week. I'll give you lectures this week and next week. After that, Chris will do that. But there will be some overlap, because I need to talk about some of those things with you with regard to the pracs. Okay, so you'll hear a few things, but that's okay. It's probably good to get it repeated. All right. So this channel here will be narrower, and the banks won't be quite as high as the channel down there, because, and I'll tell you this little saying, alluvial rivers are the authors of their geometry. Okay? Alluvial rivers are the authors of their geometry. That's a really key little saying for you to remember, because it's really what this is all about. In other words, alluvial rivers, that is rivers that are cut into alluvium, into sediment, and alluvium is the sediment deposited by rivers, as opposed to colluvium, which is material that has come down slope. Alluvium is the material that we're sitting on here, or this ground here. And when rivers cut into the sediment, as opposed to bedrock channels that are like the Barron Gorge, incised into solid rock, when they cut into a sediment or alluvium, they control their geometry, and their geometry is the width of the channel and the depth of the channel. And how do they control that geometry? Through the discharge. And the discharge is the amount of water coming down the channel. We measure it in a unit called QPEC, which stands for cubic meters per second. So discharge is the volume of water coming down the stream per unit time, past a point. Okay? Cubic meters per second at a point. So we would measure it here, and that's how we would look at it. Sometimes people talk about megalitres, but most of the time we talk about QPEC, stands for cubic meters per second. Okay?
The megalitres, is that more of a local thing with the power stations and stuff?
They may do that, yeah, but most of the time flood hydrologists will talk about QPEC. Okay, so the Barron River, when it overtops the highway and we get a big flood there, it's been quite a few years since we've seen a flood like that where the highway is cut because the Barron has overtopped it and flooded the Cook Highway. It's probably around 3,000 QPEC. Okay, measured at that point there where the Cook Highway crosses the Barron. The biggest floods we've had in Cairns in the historical record were in 1911 and 1913, and they were around about 7,000 QPECs. So we haven't had a flood as big as that since 1911 and 1913. We had 2 floods. And in those days, the Barron River actually flooded all the way into Lake Street in town and flooded what was known as Hyde's Hotel in the Lake Street Mall. So, you know, that's a big flood for the Barron River to flood. That means the whole airport would be flooded all the way past North Cairns, all the way into Cairns. That would be all under the Barron River water. Okay, the last really big floods we had here, which were nowhere near as big as that, but were in the 1970s, and apparently, I wasn't here then, but apparently you could get in a tinny at Carabonica and go all the way to Yorkeys Knob, just across the country. Okay, so that was all floodplain there. That whole area through there we call the Barron Delta. I don't really know why it's called the Barron Delta, because it's not technically a delta at all. It's the Barron floodplain, but that is its local term, the Barron Delta. So it's all that cane land stretching from Yorkeys Knob all the way really to Holloway's Beach in a big sort of triangle shape. Okay? That is all floodplain. And what we are standing on here is floodplain as well. So the floodplain is the area that gets inundated by water once the water overtops and leaves the channel. So once that water floods out of there, overtops the channel and spreads out over here, it's a plain that gets covered during floods. Does that make sense? Higher floodplains, abandoned floodplains that sit up higher than the present floodplains, are called terraces. They're older floodplains when the stream channel was at a higher elevation or level, and since then the stream has cut down deeper, it's cut its channel down deeper, and it's abandoned that floodplain and it's made a new floodplain. And so those older abandoned floodplains are called terraces. Sometimes we can have flights of terraces going up like this on either side of the channel, you know, where you can see where the stream is chopped down and chopped down. But that's what they are, they're abandoned floodplains. The channel is from the edge of the floodplain, just over here, down into and across there and up the other side. That makes the channel. And that whole area there, where we walk down off the edge of the floodplain in there and walk up the other side, we would call, during a flood, when the water gets up to the top of that channel, the top of the banks, we would call that the wetted perimeter. And the wetted perimeter is the area that is wetted in the channel during a bank full flow. I know I'm throwing a whole lot of terms at you here, but that's deliberately so, because you need to know these things. So when we talk about bank full flow, the water has filled the whole channel and it's about to spill out over onto the floodplain. That's bank full flow.
So the channel here is basically at this level.
Well, technically it would be from the edge where that tree is down, the bank of the channel, across and up the other side.
So this level is 2 different levels.
We do in this situation, but you probably find that that level over there is close to that level over there. So this has sort of been chopped out a bit. Yeah. But that's what we would call wetted perimeter and bank full flow.
So what's the difference between the wetted perimeter and the bank full flow again?
Well, the bank full flow refers to the amount of water in the channel,
Yep.
and the wetted perimeter is talking about the sides of the channel that are being touched by the water.
Yep.
The wetted perimeter will come in later during our pracs when we need to do some hydraulic measurements or some calculations. There's some very simple equations that you're going to do. They're all spelled out, written out in your prac book, and I'll go through them with you. But these are just terms that you're going to be using there. So we've had discharge, we've had bank full flow, we've had wetted perimeter, we've had floodplain, we've had terrace. Okay? So channels cut into sediment are shaped by the prevailing discharge. And the standard textbook theory is that it is the 1 in 2 to 3 year return interval flood that shapes the channel. So the flood that occurs on average every 2 to 3 years will be responsible for shaping the channel and giving it its geometry, its width and its depth. That's one of the factors that shape the channel. The other is the nature of the sediments that it has been cut into. the other is the slope of the channel, and the other is the nature of the channel. Sometimes channels can be meandering, sometimes they can be straight, sometimes they can be braided. Now, you should be getting all those definitions and views of different channels in your lectures later on with Chris. So I won't go into those in too much detail now. But if he doesn't cover it, then I'll cover it with you in class. Okay? So when I said that alluvial rivers are the authors of their geometry, when I say that, they control their geometry by the prevailing discharge. And we denote discharge as a capital Q. Just a capital Q stands as a symbol for discharge. So you might often hear people talk about or see written the Q100 or the Q50. It is the 100-year return interval flood, or the 50-year return interval flood. Now, a common mistake that many people make is that they think that that flood of that size will occur every 100 years. So if you've gone 99 years without that flood occurring, that flood will occur next year. It doesn't work like that. It's not like that. It means that on average, that flood will occur every 100 years. So in any given year, there is a 1 over 100 chance of that flood occurring. So it's a probability. It's a statistical measure. A 1 in 100 year flood means a 1 over 100 chance of that flood occurring in any given year. So you can actually get 2 100-year floods in consecutive years. Does that make sense? Exactly. The real chance of a 100-year flood occurring in a 100-year period, I think, is 63%. And I can give you the equations to show you how that works. Any of you doing, what's the subject that Will Edwards teaches? Stats. Yeah. What's it called?
Quantitative method, biology.
Bio something, isn't it? But in that, has he not shown you the binomial distribution? If you just talked about a binomial distribution? Well, the equation for the binomial distribution will show you that it's a 63% chance of that flood occurring. So I really want to emphasise to you that it is a statistical measure. It's a probability. It's not this flood will occur every 100 years. People often get very confused about that. The media gets incredibly confused about it. Okay. But the return interval flood, the shape in the channel, is thought to be about a 1 in 2 to 3 year return interval flood. So the flood that has 1 over 2 or 1 over 3 chance of occurring in any given year. A 50% chance or between 33 and 50% chance of occurring in any given year. And it is thought to shape the channel. So sometimes if you get really big floods, they will cause the channel to widen and deepen and accommodate more of the flow. So this is what I'm talking about. They are the authors of their own geometry. They do widen and deepen in order to accommodate more of the flow. And that is because the channel can erode. Because it's in sediment, it's relatively soft. It can erode both laterally and vertically. Yeah.
You know how you said that like the 1 to 2 interval flood affects the channel? Could it be like also a smaller flood, like it's less, so it drops more sediment? Wouldn't that affect it as well?
It does, absolutely it
but
does.
Not
It works the other way.
Pardon?
It works the other way.
Yeah.
People used to think that these floods just, the 1 in 2 to 3 year flood was the same all the time. It was kind of independent of time in that regard. But what we've recognised now is that is not the case, particularly in eastern Australia. And what we do is we go through what we call flood-dominated regimes and drought-dominated regimes. FDR and DDR. I know that if there's any Americans in the class, they always think of FDR as Franklin Delaware Roosevelt. So you can remember it via that, but we're not talking about Roosevelt. We're talking about flood-dominated regimes and drought-dominated regimes. And we have periods of time when we tend to get more floods. The floods tend to be bigger, and other periods of time when the floods tend to be smaller. So obviously the FDRs are the times when floods tend to be bigger, and the DDRs are the times when floods tend to be small. And during the FDRs, channels tend to widen and deepen in general. So the 1 and 2 to 3 year flood will have a higher discharge, it will have a higher magnitude than during those periods of time when the DDRs dominate. Does anyone know what might control these DDRs and FDRs in eastern Australia?
El Nino?
Yeah, El Nino, La Nina.
El Nino?
You're on the track, but you've not got the right climatic.
Southern Oscillation?
Yeah, Southern
Southern Oscillation is the same thing as El Nino. It's virtually. The Southern Oscillation is just the description, or the SOI is the index.
La Nina.
No, so that's the same thing. That's about a 2 to 7 year period.
How big the monsoons are?
Well, that on a seasonal basis, yes, but I'm talking, there's another climatic oscillation that has got a longer period than SOI, yeah, the Southern Oscillation. Does anyone know what it is? It's called the IPO, the Interdecadal Pacific Oscillation. Any of you heard of this before? Should have heard about it if you've done any hydrology and stuff. Okay, that's really, really important, the IPO. It's an oscillation in sea surface temperatures from one side of the Pacific to the other. And it also, in the IPO, it incorporates the North Pacific as well as the South Pacific. Okay? The PDO is the Pacific Decadal Oscillation, which just refers specifically to the North Pacific. This was discovered because fishermen, commercial fishermen, recognised that their catches, their fish catches off northwest USA and Canada, the Pacific coasts of those countries, oscillated on about a 20 to 30 year basis. Some 20 to 30 year periods, their catches were much bigger than other 20 to 30 year periods. So they started to investigate and saw that the fish were responding to these oscillations in sea surface temperatures. Okay? So when we incorporate the PDO, which is the North Pacific, with the South Pacific, and we don't have a specific index or oscillation name for the South Pacific, it becomes the IPO, the Interdecadal Pacific Oscillation. And if you look on the wall, just on the opposite side of the corridor from my office, and just down a little bit, you'll see a chart with all maps of Australia over, I think, over 100 years, which shows you the state of the IPO in those years. Now, here's a $64 million question for you. Does anyone know what IPO state we're in right now? You'll get the official nerd of the class if you know this.
Is it the same in North and South Pacific?
Yes? Well, hang on a minute. We're talking about IPO. So yes, the FDRs and the DDRs are controlled by the IPO, but what state is the IPO in now? And it depends if you're from the United States, then you have to. You're from Canada, sorry, but you're on the opposite side of the Pacific, so it's going to be opposite to our side. Yes, that we are in the geomorphic sense, the FDR. But does anyone know what we call it in the IPO? What's the terminology there? We talk about positive or negative IPOs, and it's based on what's happening. Those scales or those terms refer to the American side of the Pacific. Okay, the eastern side of the Pacific. Yes, good work. Well done. You're officially the nerd of the class. Good on you. Well done. You're the nerd award for today. That's excellent. Good stuff. It is negative. So you know about this, do you, from the Pacific Canada, Canadian Pacific area?
I know about droughts in Texas for the past few years.
Okay. All right. Great. Yeah. Well, they're influenced by the IPO plus other things, of course.
Yeah.
Yeah. Okay, so we have, and we went into, well, do you know when we went into the negative state?
4 years ago.
About 5 to 6 years ago. In fact, it was the year that around when Cyclone Larry came through. And we've slipped into this, and, can I even ask you any more? So we've gone into a negative state, we were in a positive state before that. When did we slip into the positive state? It's for the whole of the Pacific. So for Canada, Alaska, United States, South America, Australia, Taiwan, Japan, China, etc., Russia.
Was it about 2000?
No, got to go back further in time. In fact, it'll be before probably all of you were born.
Ah.
All of us.
1977.
It was before our time. 1977.
Definitely.
Doesn't mean you can't know about it.
No, that's before our time, wasn't it?
Doesn't mean because you're born in this year you should automatically, oh, what's the IPO? No. And we have by the way, we have these oscillations in all of the world's major ocean basins. We have the North Atlantic oscillation. We have the Atlantic multi-decadal oscillation. We have in the Southern Ocean, SAM, the Southern Annular Mode. We have the Indian Ocean dipole for, Western Australia, Indonesia, India, Africa, etc., and the Arabian countries. So all of these ocean basins show this oscillation from one side to the other in sea surface temperatures. And it affects the climate dramatically. So we have El Nino and La Nina, which tends to be a 2 to 7 year cycle. We have the IPO, which tends to be a 20 to 30 year cycle roughly. And the two interact together differently in different locations. In Eastern Australia, when we go into a negative IPO, the southern our La Ninas tend to be much stronger. Our La Ninas tend to be more effective than during times when we're in a positive IPO. So we slipped into a positive IPO in 1977. That was a major, hemispherical climate change at that time. It affected everyone that borders the Pacific Ocean. And we stayed in that until around about 2006, round about there. And now we've slipped into the negative IPO. And if we were to plot out all the big floods in Eastern Australia over the last 100 years, we can do it for Cairns, and we plot them in and plot it against the curve of the IPO, you'll see that the big floods occur and tend to cluster during negative phases of the IPO. And what I do to get with my students in my natural hazards class is I get them to plot out all of the landfalling cyclones that cross the east coast of Queensland over time, over the last 100 or so years, and plot that, the number of cyclones per year that cross the east coast of Queensland, plotted over the last 100 years, and when you plot out that curve, it fits with the IPO. So when you have a negative IPO, we tend to get more landfalling tropical cyclones. Of course, cyclones can bring heavier rain, okay, so we tend to get more floods. Of course, floods aren't always produced by tropical cyclones. Active monsoon, low pressure systems, etc., can do all that. So we tend to get wetter conditions. We get wilder weather, if you like, more extreme events. Yes, we do. That's exactly right, we do. So let's think about what's happened in Queensland over the last few years. We had really big floods in the Brisbane River, 2 years ago, 2011, negative IPO. When were the last really big floods in the Brisbane River?
70s.
Does anyone know the year?
74.
74. Guess what? Negative IPO. Between 1977 and about 2006, we didn't see any really big, super big floods in the Brisbane River. We've seen two, both of which have occurred in the negative IPO. Doesn't mean that every big flood has to occur in a negative IPO, but on average, that tends to be how it works out. So our FDRs, our flood-dominated regimes, tend to occur in Eastern Australia during negative phases of the IPO. Our drought-dominated regimes tend to occur during positive phases of the IPO. Okay? Sometimes people refer to the IPO as being warm or cool as well. Okay? And that's referring to the relative sea surface temperature on the eastern side of the Pacific Ocean. Okay, so when it's cool over there, cool equates to a negative IPO, warm equates to a positive IPO. So when the warm water's over that side of the Pacific, the other side of the Pacific, they will tend to get more rain and floods and things like that. Okay? And our side will be relatively cool. When we go through a cool phase, or a negative phase, remember the cool is referring to the eastern side of the Pacific, we tend to get more warm water here, and when we get warm water off there, or relatively warm water off there, we get more rain, and we tend to get more tropical cyclones as well. As a consequence of that, these streams respond to that. They are the authors of their own geometry, and they tend to widen and deepen. It's interesting that everyone knows Tomatoes Creek. Some of you that mightn't be from around here, but still know Tomatoes Creek. Tomatoes Creek isn't a tributary of the Barron, it's a distributary of the Barron. Most tributaries feed into the trunk stream and they supply water to that trunk stream. So downstream of that, your discharge increases, just like down here. There's a bit of a stream that comes down up through there and joins this stream down there, and from that point downstream you notice that the channel widens. Why? Because the discharge increases, because you've got a tributary feeding in to the main stream. If we call it, this one is the main stream. So Tomatoes Creek is a distributary because it doesn't supply water to the Barron River. In fact, the Barron River supplies water to it. And Tomatoes Creek formed by chopping its way headward back from the coast until it intersected the Barron River. And it did that during an FDR. So when the Barron River, when Tomatoes Creek did that, as I said, it was an FDR, it gradually chopped its way back. It was around about the early 1930s that it got up to the point near the highway. And from that point, the Barron River will start supplying some water and some sediment into Tomatoes Creek. But if we think about our FDRs and DDRs, the channels will shallow and narrow during a DDR, widen and deepen during an FDR. From the junction of Tomatoes Creek and the Barron River to the coast, which is at the northern end of Holloway's Beach or southern end of Yorkeys Beach, is 5 kilometres. From that same junction going all the way down to the mouth of the Barron, near Machan's Beach, is 10 kilometres. So it's a shorter distance to get from that junction to the coast going down Tomatoes Creek.
So more water will go that way, like will the Barron move
It will,
that
because
way?
if it's 5 kilometres from there to the coast and 10 kilometres from there to the other, to the coast down near Machan's, it's a much steeper gradient down Tomatoes Creek. Steeper gradient means faster flowing water, which is one of the velocity, stream velocity is one of the factors which controls the channel geometry. But Tomatoes Creek, over the last 30 to 40 years, has been in a DDR. And so it would have widened and shallow. But when we go into the FDRs with more floods, it will gradually widen and deepen a bit. And the more water it starts taking down off the Barron, the more it will start to become a more dominant stream. So the Barron will end up not going out at Machan's Beach in the future, will actually come out at the northern end of Holloway's Beach. It will take over Tomatoes Creek as its main channel. And the Barron River's done this a number of times in its history, certainly in relatively recent history. It's jumped to its position where it comes out at Machan's. It used to come out more over towards what we call Casuarina Point, more in towards Cairns Harbour, at the bay that Cairns sits in. So it will do that, but it will do it during an FDR, when we get more floods, bigger floods. Okay? And it's all about the channel widening and deepening. Are there any questions so far? I've thrown a whole lot of information at you. No? Everyone's completely comprehended that? Got
Still
it all?
processing.
Yeah?
Still processing.
Still processing?
Yeah.
Okay, fair enough.
Do those 100-year floods, are they larger than the 50-year flood?
Yes,
And
they tend to be. The less frequent the flood, the larger it is. So remember, it's less frequent because it's a 1 over 100 year return interval flood. So it's a 1% chance of occurring in any one given year. So the more frequent the flood, the lower the magnitude it tends to be. The rarer floods tend to be bigger floods.
so how do you know which flood it is based on the height of it?
We take a record of discharge at a point and we plot that up over time. And then we use what's called the Weibull distribution to work out our return interval. And I'll be taking you through that in class to show you how we work that out.
Don't you like extrapolate it along so you can go to like 1,000 years or something?
Yeah, that's true. But in reality, if you think about it, well, that slope, that line, will steepen a bit in FDRs, shallow a bit in DDR. Do that.
Yeah.
So that's really what's going on in nature. We tend to just put a line right through the middle of it. Okay. So these are important concepts for us to learn. Any other questions? Comments about anything? Okay then, well, to now put you into the local context here, this whole area that the university is built on in this valley here is built on an alluvial fan. These streams have incised into an alluvial fan. These alluvial fans build up when streams come down off the escarpment. They hit a change in slope and gradient. They tend to slow down, velocity slows down, and in the past, the streams have built up this very, very broad alluvial fan. It slopes gently from up there all the way down to the coast. And every valley along here is composed of alluvial fans. Really, it's a whole bunch of fans that are coalesced together to form one big-looking topographic feature. Okay? And these streams have incised into that alluvial fan. But delta tends to be subaqueous, submarine. It's spreading out into a body of water.
Snaked across the floodplain in various places doesn't make it delta.
No, not technically, geomorphologically. Delta tends to be those deposits that get put once the water goes into a lake or into a body of water, the ocean.
Build up with sandbanks and that, and end up with loads of.
That's right. Yeah. So these alluvial fans, they occur all the way along the wet tropics coast, in all of the valleys. And we see some really big ones bordering the Mulgrave River and other big rivers. The area that Woolworths is on at Smithfield, you know, when you're the roundabout there, the Bunnings, road up to Caloundra, etc., and you drop down past the Shell service station, and you're going down slope till you hit that creek down there. What's that creek's name again? I forget the name. But the creek that goes and floods the ski park every time you get heavy rain. Well, that area that Woolies is built on is part of this same sort of fan that this is. It's not the same fan per se, but it was deposited at the same time. So that's the fan there, okay? And the Barron River has chopped out that fan, and you go down onto the area up to the level that Yavakai and Sky Rail and the cable ski park is on. So that then becomes the floodplain, the modern day floodplain. But these fans tend to have been incised into, chopped out, and parts have been left up higher. They look like terraces, but they're technically sort of terraces cut into the alluvial fan or made from the alluvial fan. These alluvial fans are very extensive throughout this area. In fact, when we drive to Port Douglas, you can drive along the road, and on your left-hand side you can see big high exposures of these fans. They stand between 8 and 10 metres high above the road up there. And so they were once very extensive. They extended right out onto the continental shelf. So that tells us if those fans are right near the beach there, the coast, as you know, the coast can be really close driving up there, and they're 8 to 10 metres high, if you extrapolate the surface of those fans, you'll see that they extended right out onto the continental shelf, which tells us what? About when they formed.
Tidal height for the sea level.
They formed before the sea level rose?
That's right. They formed at a lower sea level. When was the last time that sea levels were low?
20 years? Wasn't it?
6,000 is when they got up to their present height, roughly.
Well, 6,100.
No, sea levels were about 120 metres lower about 20,000 years ago. Okay? About 20,000 years ago. Or about 18,000 radiocarbon years. A radiocarbon year is different to a calendar year, for various reasons that I won't go into. But about 20,000 human calendar years ago, sea levels were about 120 metres lower than they are now, which puts them, sea levels, right down the continental slope, right down. So clearly these fans probably formed, the first assumption is that they formed when sea levels were lower. The last time sea levels were lower, around about then. So you could assumed that they were probably somewhere in the ballpark of 20,000 years ago that they were deposited. But we went and dated them anyway, so we wanted to check. And so we dated them using optically stimulated luminescence. Any of you know what this is? OSL for sure. It dates the time when sand grains were deposited and buried. Okay? A very famous physicist once took a very precious gemstone with him to bed and held it against a very warm part of his body throughout the night. And then he looked under the covers and lo and behold, the gem was glowing. Any of you who do geology and mineralogy will know that minerals have their own unique luminescence qualities. Different minerals and gems will give off a different colour light when they're heated. Any of you know about that from geology? You know, when you identify minerals, you have your cleavage, your streak, all of those properties. None of you do geology.
First year geology.
Huh? You do
I think
geology?
most of us have done first year geology.
Okay, so you would have learned about how to identify, you know, your scratch plates, you've got your Mohs hardness and all this sort of stuff. Well, one of the properties is their luminescence. So when you heat them up, they give off a light. Different minerals give off different coloured lights. And what's going on there is it's making electrons jump from what we call deep traps to shallow traps. By their moving, they give off light. That is the luminescence part of this dating technique. When quartz gets transported and exposed to sunlight, its luminescence signature, we say, gets zeroed. But when it gets buried in the ground and it's not exposed to sunlight, background radiation from say potassium or small amounts of uranium or thorium in the soil, in the clays, etc., bombard that quartz grain and cause those electrons to jump to different places in the crystal lattice. And if you sample that ground without that dirt, that soil, sediment, without exposing it to sunlight, you can take it back to the laboratory and you can figure out how long that sand grain had been buried there for, based upon the number of electrons that have jumped from the shallow traps to the higher order traps. And what we do is, with optically stimulated luminescence, we take it into a special laboratory, we bombard the sand grain with a laser beam, and it gives off light. The amount of light it gives off is roughly equivalent to the amount of time it's been buried there. So it's a very, very good dating technique. It's not like radiometric dating techniques, which date the decay of particles. Okay? This is completely different. And it's not like radiocarbon dating, which tends to date the time of death of the organism. So if you find a shell or a piece of coral and it gets deposited, the date of that shell or coral mightn't be the date that the sediment was laid down there, but it's the date of the death of the organism, which we always assume happened shortly before it was deposited, but you can't be really sure of that. But this one does this. So we used OSL dating, and we found that these alluvial fans were deposited between 28,000 years ago and 14,000 years ago in two stages. There was one from about 28 through to around about 20, and then another phase from about 18 to 14. And lo and behold, when you go and check up with the pollen record from Lynch's crater on the tablelands, which gives us a history of vegetation and therefore climate throughout the area, we find that the driest period of climate here was exactly between 28 and 14,000 years ago. So these alluvial fans were deposited in response to the drier climate at the time. The sediment was being liberated off the hillsides. The streams didn't have the capacity to carry that sediment because their stream discharges were generally lower. So they deposited the sediment and built up, aggraded the valley floors and built up these fans. When we went out of the end of the Pleistocene ended 10,000 years ago, and we're now in the Holocene. After the Pleistocene and the last glacial maximum, which is at 20,000 years ago, so after about 14,000 years ago, climate started warming and becoming wetter, and the streams no longer needed to deposit their sediment. They could carry that sediment out down to the base and down to the ocean, and the streams started incising into these fans. So that's how these fans have come about. They are a response to a major global climate change. A global climate change, part of the glacial cycles, the glacial interglacial cycles. And they occur during the driest phase of climate. So you can see that rivers respond very dramatically, at least over those timescales, to climate and climate change. Does that make sense? So that's what's going on here. All through the wet tropics we see these fans, they all date to the same age. We even went up to the back of the Burdekin in the wet dry tropics, up on the tablelands, and found where there's no big hill slopes up there, it's all just flat country, the big terraces that are formed up there, big deposits, are also dated to exactly the same time. So we've published a series of papers on that, which you can find in the literature. Okay? So if you want to go and look up that stuff and get all the details, you can find it in the various journals.
Would the fans be here? How deep they actually
I don't know, we've not drilled right down to them. We mainly worked off creek bank cuttings and took our samples that way. But the fans certainly in the Mulgrave River are 8 to 10 metres. Okay. More than, no, they're probably 20 metres. 20 metres, yeah. The actual banks of the Mulgrave River are 8 to 10 metres high. So that's the local, relatively recent geological history of this area, and that's what these streams are cutting into. So they're now in a phase where they tend to be cutting into their plains, their floodplains or alluvial fans, over the longer geological time. But remember that they also change their geometry, less so, but nonetheless change it with width and depth in response to things like the FDR and the DDRs and local and individual flood events as well. So if we had a really big rainstorm, we had 500 millimetres of rain overnight just up there on Saddle Mountain, then probably this creek would widen somewhat. Its banks would get eroded and maybe deepen a bit. Maybe it probably widen more than deepen. So that's what's going on with these streams here. Does that make sense? Yeah.
trying to work out how to say it. Obviously, as you get more water coming down the wider, deeper, less water, shallow, but you'll never get it narrow. You can't narrow.
No, you can't close the channel.
Yeah, they can't close the channel. You can get it shallow. So why aren't
well, you can close the channel. I'll tell you how you can close the channel. What happens is the streams can avulse. They can jump from their position there and they can jump over to here. And then gradually that channel will get filled in with sediment. But that's how it would do it. But no, it wouldn't ever slow down to the point, if it slowed down to the point where it had no water going down, then it's not carrying any sediment to be able to reduce the geometry, the volume of the channel. So now I've just told you what a floodplain is, what the channel banks are, the bed of the channel. So from a geomorphological perspective, that's how we see it. Make sense? Vegetation that grows along the edge of the channel on the bank is called riparian vegetation. Extremely important for a whole range of ecological, biological reasons, plus geomorphological and geological reasons. Critically important. I'm going to tell you a story now about the law. The law in Queensland in particular. We have a thing called the Water Act. And in that act, it specifically states what a channel is. It says a channel is defined by the normal flow of water. The normal flow of water. The channel is owned by the Crown. It's owned by the Crown, the government, state government. So anything in the channel belongs to the Crown. So obviously not in this channel, but if you've got a really big river, like the Brisbane River, the sand in the channel, which is a valuable resource, is owned by the Crown. And also there are various policies and legislation which say people aren't allowed to clear vegetation so many metres back from the edge of the bank, the channel bank. It's riparian vegetation that has to be left there. That's what the Act says. In the late 1990s, Woolworths wanted to build a supermarket at Maleny in the Sunshine Coast hinterland. Do you know Maleny? Maleny's a really nice little village atmosphere. It's got quite an alternative sort of, population in it, and it's beautiful. It's a lovely little tourist area. And these people didn't want a big Woolworths in there. They said, no, we don't want that. That destroys the character of it. So they went to the Queensland government, which was then the Department of Natural Resources. You know how these government departments change every few years. DNR as it stood then. The geomorphologist in DNR came out, looked at the channel and said, well, you can't do it. You want to build too close to the channel bank. You can't clear that vegetation. It all says that. So the company, Woolworths, said, we don't accept that. We want to build right channel. In fact, they wanted to build in the channel. They wanted part of their building to go into the channel. And DNR said, no, we're refusing your application. So they refused it. So they said, all right, we'll take you to the Queensland Land Planning and Environment Court. And they did. In that court case, you can go and read all this because the judge's decision is online. In that court case, they hired an engineer who I know, name's Neil Collins. I've been in court with him myself in the past about planning environment issues. I didn't steal something or beat up an old lady or anything. I don't do that. So it's a planning and environment court issue, but no, I wasn't involved in this case. In that, Neil Collins, engineer, said, he produced a report which said that the normal flow of water can be defined statistically. And normal in this case means anything that occurs more than 95% of the time. Because often we take 95% as our statistical margin and measure, you know, that we say okay. And so what he did is he got a year's flow data and showed that 95% of the time the water in the channel excuse me, is kept within a little channel that's inset within the other channel. Often channels, you go off the floodplains into the channel and you have what's called a little inset channel in there. He showed that 95% of the time the water that goes down that channel is confined by the inset channel, not by the bigger channel. 5% of the time did the water come out of that little channel, flood into the major channel or flood onto the floodplain. So he said, well, the normal flow, statistically speaking, is defined by the Q3 month. That is the 3-month flow. Okay? So, like here, if we were to say what 95% of the time, the water that comes down there is about that wide. It's only on those big events in the wet season, and indeed this year we've hardly had any water come down these creeks because it's been so dry. So the judge thought about this and said, well, okay, I accept that. So now we have a legal definition of a channel and a floodplain and riparian vegetation in Queensland, which isn't consistent with the rest of Australia. They all tend to use the geomorphological definitions. So DNR lost their case, Woolworths won their case. They've now got a Woolworths in Maloney. But we now have a new definition of a channel in Queensland. So now the sand in the channel no longer belongs to the Crown. So it can be mined. So then after that case, a big sand mining company wanted to go and mine the South Brisbane River. DNR said, no, that's the channel, that belongs to the Crown. They said, we'll take you to court. And we'll use the precedent set by the Maloney case. And they then went and showed that that isn't the channel anymore, therefore it's not owned by the Crown, and they were able to mine sand out of it. So in Queensland and Queensland only do we have a new definition of a channel, all based upon the word normal in the legislation. If that word normal, the legislation was written differently, written by a geomorphologist or advised by a geomorphologist, we wouldn't have that situation in Queensland. It's an interesting scenario, and it's a real scenario. I've written about it in articles, and you can actually go online and read those judges' decisions about that. But you can see where the law and our geomorphology can differ quite a lot, and it can mean a lot. It can mean a lot of dollars in terms of resources, either for the state or for private industry, all because the way that the Water Act, whatever year it is, I forget, was written. Okay. So, different definition legally. Sorry? I don't think so. I don't think so. I don't know exactly. I haven't been there since then. I've been to Maloney plenty of times, but not there since. I haven't seen it. So I think it was a corner of the building. But by the way, now you can go and strip all this vegetation off the banks here. It's perfectly legal because that isn't the channel anymore. So that no longer legally is riparian vegetation. You can just remove it. knock it down. You don't need permission. If it's your land, you can knock it down. It's completely stupid.
They'd go for the damage that can be caused either once in a 20-year occurrence or something, as a measure, which makes more logical sense. But I'm now talking about the law, and I'm not looking.
The legislation says normal flow of water.
So like where it says it doesn't work on back from.
The channel bank. It works on channel bank. So all of this is not right here in vegetation legally. It's only the stuff that goes in there that becomes right. And this, by the way, isn't a floodplain. The floodplain is down in there. See?
That's the legal definition.
That's the legal definition, but if you ever want to make a decision about things, and it goes to the Planning and Environment Court, that's the way it happens. That's
So
what
how
it is.
come you still need leases to go mine stuff?
Well, you do need leases because, that's just the way the government system works.
Yeah,
but
that's a
you
different
can't,
aspect.
if you're granted that lease,
You can mine whatever you want.
yeah, that resource can now be bought.
Yeah. But there's a code that you have to, you have to abide by. You still have to abide by all those rules, even though that one law kind of half overrides it.
Yeah.
Because you're not allowed to touch certain bits of vegetation in the code, and you're not allowed to bank the river. Like, you're not allowed to put a dam straight across here and have all of it there.
No. Yeah.
But technically, it's not the normal stream flow. Like, it's not still classified, so you could do that.
Yeah. If you wanted to challenge it in the court, you could. And that will remain the case until that legislation is rewritten.
Or someone sets a new precedent.
Why isn't someone onto that?
Sorry?
Why isn't someone sorting that out before something disastrous environmentally happens?
Because politicians, I don't know. Politicians are the ones who introduce new legislation, and it's up to the politicians who advises them on what they should say in the legislation.
So
I wrote an article calling politicians and geomorphological blunders, and I published that. And I just had a real go at the legislation and the pollies about all this, but I'll blow it, I'll be damned, But I'm going to say it because there's lots of examples like that. So
it's the amount that they measure the normal flow off is just a 1 year period, or just that 3 month?
1 year period.
So it's just 1 year period that they measure that. So okay.
So if you then went and got this year's flow for this creek, it'd be like this wide.
Yeah.
So should someone go and do like a huge amount of statistical data and say this is actually the normal flow, and you can change it again?
It might do, but probably not by a lot.
And which year did they pick?
I forget. I don't know. We'd have to go back to I don't think that the year that they chose was in the judge's decision. The judge's report, his or her decision, is published online. But all the details of the presentations by the barristers and the expert witnesses, etc., don't get published online.
So it doesn't have to be the most recent year that they take these measurements of. It can be any.
It could be anything. It's whatever the expert witness presents to the court, and whether the judge is willing to accept that. And when you've got really silky smooth barristers that are in there guiding all this through, it's very difficult to argue against that. I've been in these courts and I've been up against these absolutely amazing barristers that they're masters of language, and they just can twist things around beautifully but deviously, and it's just amazing. They're so skilled. I'm just in awe of them, the way they do things, but that's what happens. So that's an interesting case anyway. That's the Queensland. But I'm talking to you about the geomorphology here and what's going on. So let's now just walk down to the bank and have a bit of a look at what's going on